Yeah, on this video, we will talk about electrical motor or continuous drive actuators. The electrical motor's construction. First, the electrical motor works based on the electromagnetic. So, we will talk about the magnetic field and the other of concept of electromagnetic. Magnetic field. Magnet is an object that has a magnetic field. The magnetic field is represented by imaginary lines called magnetic lines of force or magnetic field lines, or we can call it flux. And this is the magnetic line or the magnetic field. And then magnets can be generated by electric current. Around a wire that is given an electric current, a magnetic field. It's called electromagnetic field or magnetic field. And this is the illustration how the magnetic field created or generated. And we can see this is a battery, and then the current can generate the magnetic field. If the line of magnetic force is cut by a conductor or the coils, then at both ends of the conductor there will be an electric potential difference which causes an electric current. This potential difference is called the induced electromotive force. This is the illustration of moves a magnetic field through a stationary conductor. And this is the movement of a conductor through a stationary magnetic field. And then this is the illustration of the movement, the transmitter movement in rotating manner. And then in magnetic induction, factors that determine the magnitude of the induce is first the number of turns of the coil. This is the coil. It's determined the magnitude of induction. And the speed of entry and exit of the magnet into the coil, and then strong the magnetic field. And then this is the electrical equipment that works on the principle of the electromagnetic induction. First is transformer, and then generator or dynamo, and electric motors. First, the transformator. The transformator is the device used to increase or decrease the AC voltage. The working principle of the transformator is electromagnetic induction. First, this is the primary coils, and this is the secondary coils, and this is the magnetic fields created by the electromagnetic induction. Transformator have two types. First is step-up transformator. The step-up transformator is used to increase the electrical voltage. The primary coil turns less than the secondary coils, and the primary voltage is less than the secondary voltage. And the second is the step-down transformer. This is the electricity in this coil comes from the national grid, and this is the electricity in this coil goes to home and shop, for example. In the step-down transformer, the primary coils turns more than the secondary coil. Okay, we can see in this illustration. And the primary voltage is greater than the secondary voltage. This is the transformer equation. We can see this is for the primary coils, and this is for the secondary coil. This IP is the primary electric current, and NP is the number of primary turns, and NS in here is the number of secondary turns. ES is the current of the secondary coils, or the secondary electric current, and VP in here is the voltage, primary voltage, and VS is the secondary voltage. The equation is VP per VS equals to ES per EP equals to the NP per NS. The efficiency of the transformer, in reality, there is no ideal transformer. The power that enters the transformer is not the same as the power that goes out due to losses in the transformer. The transformer efficiency is right as P in here is efficiency of the transformer efficiency, and the PS is the power of primary, and PP in here is PS is a secondary power, and PP is the secondary power. The PP is the primary power, and multiplied by 1000%. This is the transformer in electric transmission. This is a generator for in bahasa SPLTA, pembangkit listrik tenaga air, and there's a trafo step up, and then the voltage is distributed by the tower, and then it will be fit into the trafo step down, and from the trafo step down, the voltage is distributed to our home and the building. And so, for example, this is the question for you that you have to answer. A transformer with a turns ratio of 10 divided by 2 is connected to a 100-volt source to power a 25-watt lamp. Calculate the electric voltage absorbed by the lamp and the current entering the transformer. Assume an ideal transformer. A transformer whose efficiency is 80% produce a voltage of 50 volts and a current of 10 ampere. In the secondary coils, if the primary coil of the transformer is given a voltage 200 volts, what is the current string? Okay, try to answer this question by yourself. Okay, now we will talk about the generator. Generator converts mechanical energy into electrical energy using the principle of electromagnetic induction. The type of generator is a DC and AC generator. The induction electromotive force is based on the law of Faraday, which is the induced electromotive force is electromotive force that arises in the coil. This force includes a certain amount of magnetic flux. The induced electromotive force only occurs when the magnetic flux is present in varying amount. This change in the amount of magnetic flux must occur over time. For the Faraday, the quantity that affects the appearance of an induced current is the magnetic flux. Magnetic flux is the number of magnetic lines of force that pass through a plane perpendicular to a certain area. This is the illustration of the inductive electromotive force. We can see that the delta is equals to B dot A dot cos theta, whereas delta is a magnetic flux in Weber, and B is magnetic field strength in Tesla, and A is the area of the coils, and then epsilon in here is in bahasa is gaya gerak listrik. Gaya gerak listrik is electromotive force at the time of induction in volt, and N in here is the number of coils, and d delta dot dt per dt is the change of magnetic flux in Weber per second. And this is the generator DC to produce direct current. This is the magnetic, and this is in here is the coils, and this is the brass carbonic brass, and this is the commutator, with the brick rings, and we can compute the electromotive force as equals to the minus N dot A dot B omega cos omega T. And this is the illustration of the generator DC. they will create the waveform in the half of waveform. So we can see this is the pulse for north and for the south, and then it will be created when the what's in when the coils here, when the coils is turn 90 degree, so it will be create half of waveform, and then they come back to the in 180 degree, so it will be created at the other half, and the result is we can see at this waveform, and then it will be move or rotate in 90 degrees, so it will be created one of waveform, half of the waveform, sinusoidal waveform, but half it cut in half of the waveform. And for the AC generator, we can see there's rings, two rings or double rings, and still have the carbon brush. And this is the coil, and this is the magnet to create magnetic fields. So in AC generator, we can see it will be create a full sinusoidal waveform. This sinusoidal waveform is for one pulsar, is from the 0 degree, and they move into 90 degree and move again to the 180 degree and move again to the 270 degree and move again in the same position as the 360 degree. And electric motors is operate or work use the principle of the electromagnetic concept. So this electric motor is converts electrical energy into mechanical energy with the principle of the electromagnetics. And mechanical energy is used to turn pump, blower, fan, and mixer, electric drills, and so on. And we can see this the classification of electric motor. They have two variables. First is AC motors, and then DC motors, and then the synchronous. For the AC motors is they have the synchronous AC motor and induction AC motors, and for the induction is divided into two kinds. There is one phase and three phases. And for the DC motors is divided into the sparkly excited motor and self-excited motor, and For the self-excited motor is divided into the serial motor, hybrid motor, and shunt motor. The motor working principle. A magnetic field is a vector field that describes the magnetic influence on moving electric charge, and then the electric current and magnetic materials. A moving charge in a magnetic field experiences a force perpendicular to its own velocity and to the magnetic field. A permanent magnet or the magnetic field pulls on ferromagnetic materials such as iron and attract or repels other magnets. In addition, a magnetic field that varies with the location will exert a force on a range of non-magnetic material by affecting the motion of their outer atomic electrons. Magnetic fields surround material and are created by the electric currents such as those used in electromagnet and electric fields varying in time. And this is for the permanent field and magnetic field. Since both the strength and direction of the magnetic field may vary in location, it's described mathematically by a function assigned a vector to each point of the space that called vector field. This is the vector field. And in electromagnets, the term magnetic field is used to two distinct but closely related vector fields denoted by the symbols B and H. And then magnetic fields are produced by moving electric charge and the intrinsic magnetic moment of elementary particles associated with a fundamental quantum property in their speed. Magnetic fields and electric fields are interrelated and are both a component of the electromagnetic force, one of the four fundamental forces of the nature. Magnetic fields are used throughout modern technology, particularly in electrical engineering and electromechanism. Rotating magnetic fields are used in both electric motors and generators. The interaction of the magnetic fields in electric devices such as transformer is conceptualized and investigated as magnetic circuit. The magnetic force gives information about the charge carriers in a material through the Hall effect. And this is the working still in motor working principle. They use Fleming's left hand rule. If we stretch the first finger and the second finger and the thumb of our left hand to be perpendicular to each other, and first finger represents the direction of the magnetic field. The second finger represents the direction of the current. Then the thumb represents the direction of the force experienced by the current carrying conductor. In the left hand rule, we can see that the thumb is represent rolling force and the index finger represent the magnetic field, and the middle finger represent current. And then when the armature winding is connected to the DC supply, for example, for the DC motor, and the electric current set up in the winding, the permanent magnet or field winding electromagnetism provides the magnetic field. In this case, current-carrying armature conductors experience a force due to the magnetic field. According to the principle stated above, the commutator is made segmented to achieve unidirectional torque. Otherwise, the direction of the force would have reversed every time when the direction of the movement of the conductor is reversed in the magnetic field. This is how motor works. And we can see this is the magnetic vector, and this is the Lorentz force, and this is the electric current, and this is the magnetic induction T, and then this is the electric current in ampere. So we can get F is equals to electric current dot wire length dot the magnetic induction SP ELB sin theta, and theta in here is angle between P and I. And then this is the motor working principles. They use the polarity of north and south that change when the current is changed the direction of the current. And we can see this is the illustration. And this is the illustration of the motor. In this case is DC motor. And they have the armature. Armature is armature coils that consists the commutator and brushes. And then this is the commutator. Commutator used to convert the AC induced in the armature into the DC, and brushes transfer the current from the rotating part of the motor to the stationary external load. And then the armature plays between the north and south pole of the permanent or the electromagnet. A simple DC motor uses a stationary set of magnets in the stator and coils of the wire with the current running through it to the generated and electromagnetic fields aligned with the center of the coil. One or more windings of insulated wire are wrapped around the core of the motor to concentrate the magnetic field. And then The armature plays between the north and south permanent and electromagnet. When the armature windings connect to the DC supply, an electric current set up in the winding. Then permanent magnets or field winding electromagnetism provides the magnetic field. In this case, current carrying armature conductors experience a force due to the magnetic field, according to the Fleming left-hand rule. The commutator is made segmented to achieve an directional torque. Otherwise, the direction of the force would have reversed every time when the direction of the movement conductor is reversed in the magnetic field. This is the illustration of the rotation in armature and commutator parts. Okay, and first, this is the current of DC motor. We can see from the picture, this is the electric current supplied externally through the commutator. And then the commutator reverses the direction of the current every half turn to keep the torque turning the coils in the same direction. It occurs when the electric current flows through the coil in a magnetic field and the magnetic force produces a torque which will turn the motor. When electric current flows through the coil in a magnetic field, the magnetic force will produce a torque which will turn the electric motor. The motor torque is proportional to the magnetic field. The magnetic field is directed from the North Pole to the South Pole, as we can see at this figure. This is the magnetic field will produce a torque which will turn the electric motor. When a magnetic field flows through a coil in a magnetic field, the magnetic force produces a torque which will rotate the motor. Okay, this is for the current, and this is for the magnetic, and this is for the force. So the magnetic style is defined by F equals to E dot L dot P which acts perpendicular to the wire and magnetic fields. And then when an electric current flows through the coil in a magnetic field, the magnetic field will produce a torque which will turn the electric motor. Now we can see in here, this is the first state and this is the next state. They give a movement that different in the alpha for the degree of movement. And then we can see that the area of the coil is defined by A equals to L dot W. And Then we can calculate the torque equals to the force. The force is in the bottom. Go to the bottom, and then multiplied by the force arm is equals to ELB dot W per 2 sin theta multiplied by 2 shape or 2 phases. And we can write as ELBW sin theta is equals to E dot B dot A sin theta. And this is for the upright coil. We can see the differences. P and coil make movement of alpha, and P with the upright coil is make the theta movement. To maintain the reversal torque, the commutator changes the direction of the current at the point when the torque is 0. This is the torque of DC motor, and a torque that varies sinusoidally with respect to the coil angle. The DC motor produces an arbitrary torque, and we can get the force as W per 2 cos theta is equals to W per 2 sin theta. And this is the illustration of the force arm. And this is the vector of P, and this is for the force, positive force and the negative force. And this is the movement of the coil. And next, based on the characteristic of incoming electric current and the operating mechanism of the electric motor, there is two types of electric motor, is AC motor and DC motor, and we will talk about these two of motor in the next week. Okay, this is the end of the working principle of the electrical motor. I hope this video will be useful for you all. Okay, thank you. Assalamualaikum warahmatullahi wabarakatuh.